So, today we will just see the classification. So, the piles I did not go into too much of the material classification, because in olden days people used to use timber piles, concrete square precast piles, which are low load carrying capacity for onshore structures. You might have seen in many industrial applications, normally people use precast concrete piles of smaller size, maybe 200 mm by 200 mm square size, or maybe 300, but not more than that. But in some cases we also have used precast circular concrete piles for marine applications in the smaller water depth, but not very common because of the complexity during installation. The precast concrete piles, when you are driving, it may actually crack depending on the resistance of the soil. So, commonly used piles are steel or concrete. Concrete also is used, but mostly cast in situ. So, if you have a precast concrete piles or a steel tubular piles, you need to drive into the ground. So, when you are doing that, the erection of the pile into the soil by penetrating, by displacing the soil that is supposed to be occupied at the location of the pile. For imagine you take a 1 meter diameter shaft, circular, square, or whatever cross section, you try to drive by means of hammering at the top. When you do that, what happens is the soil is getting displaced. So, during that process the soil gets densified in and around the pile surface, which actually makes slightly better in terms of capacity. So, that is why we call it displacement piles, which are better than the non displacement piles. Basically you just do a boring in the ground and take the pile and erect it inside, and you leave it. You can just leave it without doing anything. Over the period of time the soil may come and get it contact with the pile, or you can create an artificial interface. After making a hole, you put the pile inside and then just do a grouting interface. That means the pile to the soil is connected by a better material like grout, which gets bonding. So, you can either do that. So, basically what is the difference between the displacement pile and non displacement piles? One of them is creating better characteristics of soil, the other one may be degrade. During the process of drilling, you are disturbing the soil, you remold the soil. So, it may take several months and years to get back its original quality and characteristics. But then depending on the situation we apply each one of them. Most of the time we use driven steel tubular piles beyond certain water depth because of the strength requirements. For example, if you have 10 meter water depth, maybe any pile can work, but if you have 20 meter water depth, maybe making a concrete pile to take the slenderness and the strength characteristics, you may require a very large diameter. For example, 2 meter diameter may be difficult to construct, and that is why at that type of water depth you go for steel pipe piles, which you can make 1 meter, 2 meter, 3 meter, any diameter you can make is quite easy, because you are going to take a steel plate. In terms of non displacement piles, you can use cast in situ concrete piles, which I think we described in the last session, how a cast in situ concrete pile is being erected at a site. You make a driving of a casing and do a boring, pour concrete after placing the reinforcement with and without the liner. Sometimes what happen, people want to economize, while the concrete is being cast, they actually slowly pull the liner upwards. You drive the liner, bore it, put reinforcement inside, and just pour the concrete in stages, stage 1, stage 2. When you reach certain stage, you just pull the liner up and then put the second stage and liner up. So, once the concrete is set to a reasonable extent, you pull out the concrete, pull out the casing fully. So, you can reuse the liner for another place. It does two advantages. It actually creates an interface with the concrete to soil directly, number 1, and also you save the material for the liner, because you are not going to include the liner in the structural calculation. It is only a very thin plate, and basically can save some material. But again, there are advantages, disadvantages, because when you are pulling out the casing, you may actually disturb the concrete itself, which is not very good. Sometimes we do not recommend. So, both cast in situ piles with and without liner, the calculation for the soil capacity is different, because we are now looking at the soil to pile interface. If you have a steel to soil interface, is different than concrete to soil interface. Which is better? For sure, concrete to soil interface is better because it's rough and the surface is not very uniform. So, the interface is going to give you a increased soil resistance. Mostly we will not go into calculation of bored cast in situ and drilled and grouted piles. Basically, it will not be applicable to the offshore platforms, whereas we will use the driven steel tubular piles, in fact 100%. You will not even think of using concrete piles for offshore platforms. Concrete piles are purely applicable to the coastal and near coastal structures of smaller water depth and maybe reduced loads, but for offshore structures, even if it is located in 20 meter water depth or 30 meter water depth, we will not use any other piles because the magnitude of loading is larger. I think that gives you an idea between a displacement pile and a non displacement pile. How and why we need to know this is to get an understanding of the soil behavior. Here you are disturbing the soil, where the other one is your better densification, especially in the coarse grained soils. A typical picture, I just wanted to show you how soil can vary along distance, because we need to make a decision, how much information is better. More information is good, but then it becomes time consuming and then also expensive. So, if you are constructing a bridge, say 10 kilometer bridge, how many locations you want to do a bore to find out the soil strength along the length is to be determined. You can say every 10 meter, that means 10 kilometer. If you do it every 10 meter, it will become separate project for borehole investigation itself. It takes a longer time. So, what we need to see is you identify certain coarser spacing, look at the soil profile. For example, you look at this picture, you can see here layer, there are 3 layers distinctively. One of the layer is intermittent, basically the top layer is not continuous over the length, but the second layer is throughout the length, and the third layer also, and varies considerably. You can see here one location is about 50 meter depth, the other location becomes 40. So, there is a considerable variation, but after getting this profile, you could easily find whether you need intermediate borehole or not. Sometimes you can make a decision if it varies very considerably. For example, in the starting you make every 1 kilometer boring and find out if the variation is almost uniform, maybe you can say you do not want to do intermediate borehole. But if there is changing in profile, changing in characteristics, then you do the borehole at the middle or somewhere you can decide. But that such problem is not there for offshore structures. Mostly our structures are isolated. For example, offshore structure is based with this 50 meter by 50 meter. Within 50 meter, if a soil changes, then it is a bad luck, but most of the time we do a borehole at the center of the structure where you want to construct. So, typically a profile needs to be obtained if you are having a complex of structures. For example, 3 or 4 structures in the region, you collect information from structure 1, structure 2 and structure 3. You look at a profile how the soil changes, then you can interpolate. The idea of whole activity is to make sure that the information at this location we do not know, but what we have done is based on the borehole on the left side, borehole on the right side, we think the soil could be of similar characteristics, variation could be like this. It may or may not, you actually can change from here to go like this and come back, but nobody knows, but that is the best possible assumption that we can make. So, the closer the intervals of the borehole, you can get a profile reasonably correct, because we are going to use this information for foundation design. Similarly, if you look at another site on an onshore site, you can see here some places the pockets of clay is larger in thickness, in some places it is not even there, some places very thin. So, you can see here this blue color, the pockets of clay is sedimentary in nature, probably happened several years back, and deposition of sandy material on top. This is all just, this is a very close to Ennore port, one of the new port that is being planned to construct. The soil investigation reveals that there is a packet of clay varying in nature spread over all the area, and the top 3 layers of sand over a period of time. You can see here dense sand, medium dense sand, and then beach sand, loose sand. So, deposition keeps happening, and that is the characteristics of sedimentary material near the coastlines. So, you can see there. So, basically with this, do we want to continue with the construction, whether where you want to finish the pile, whether you want to stop the pile here or want to stop the pile here, needs to be decided. So, this gives an information that the clay layer is going to potentially create a problem if you happen to terminate your pile in that layer. So, that is exactly why we need to do more number of boreholes, because if you have done only one borehole at this location and it happened to be at a location where there is no clay layer and you think it is representative of the whole site, and construct the foundations everywhere and terminate the pile foundation at that level, then you will end up in lower capacity than what actually you predicted using the properties derived from one of the borehole. So, the danger is very imminent if you do not have enough information, especially when you have the structures spread over a larger area. So, that is why borehole investigation or the site investigation becomes a predominant component in the foundation design. So, how do we do the design of foundations? There are several methods which are recommended in the past by codes, by experts. One of the best method, because now by this time you should have understood the variability of soil as a material and the characteristics changes with respect to place, with respect to time to some extent due to degradation, and the best method is to construct the structure and do the testing. For example, you construct the foundation itself, prior to constructing the superstructure you do the testing, and once you establish the relationship between the load and its displacement characteristics of the prototype, I think that is the best form of proving that the foundation has the sufficient capability and the capacity to receive and transmit the loads to the foundation soil without excessive deformation. But how many of those things you can do? For example, you take a jacket structure, you have say 4 corners, 4 pile foundations, and you need to test 4 of them. If you want to get 100% surety that the structure is safe or the foundation is safe, you need to do all 4 of them. But if you have onshore structure, for example, industrial building having several hundred piles, you may have, if you look at some of the structures on land, you will have several hundred piles, and if you have to test all the piles in that particular site, it may take a lot of time, lot of effort. So, what we normally do is we do the testing of samples of piles. Out of 100, you do testing for 10% of the piles. Pick and choose the location of piles. For example, you have a grid of piles, you select several locations which will represent that particular locality and then do the testing. Once you do one of the pile tested, that information can be used to prorate the design of new piles. For example, you do the testing of one pile at a particular location and site, gather information with regards to the load carrying capacity with respect to the displacement, use that information for your future design, because you might have designed the foundation using these characteristics derived from borehole. You have taken a sample, taken to the laboratory and tested, and you have derived some strength characteristics similar to steel. Steel for your design purpose, you have a yield strength as a design characteristic. Similarly, you can derive some design characteristics which we are going to discuss in the next few hours. So, use that information to design purely based on borehole. After that, you have done the testing and compare the capacity. You have done your calculations for 10 meter of depth of penetration or 20 meter of depth of penetration. Some capacity you have calculated based on what you have understood from the laboratory testing characteristics, plus your understanding of the soil and applying mechanics principle of load transfer either by shear or by compression. You calculated a capacity based on the theoretical methods using the results from laboratory and the field testing, and now you have constructed that foundation, done the testing, you compare these two capacities. If they match very well, is very good, because your assumptions in your analysis or your assumptions in your calculation is matching well with the behavior at site. If it does not match, then there is a corrections to be made. What we do normally is, you take the correction factors back to the engineering room. If the capacity predicted is higher, you correct it to bring down. So, you will go back and change the parameters of the strength of the soil iteratively, because you do not know which layer has contributed higher or lower, unless you have the layer wise result, which is very hard to get, because the pile load test will not reveal such type of information, because you have constructed the pile to the total depth and then you have done the testing. It is not like every time you drive little bit do the testing, you are not doing that, which is also not feasible. So, that is why testing based method is very helpful, because you collect information from prototype testing, use that to correct your design parameters, calculations backwards, again come back and find out what is the penetration required. For example, 20 meter penetration originally I have assumed, I have calculated the capacity as 100 tons, and I have installed the 20 meter penetration pile, did the testing, capacity comes to be say 80 tons. How do we say that 80 ton? Basically acceptable displacement. The capacity can be larger if you displace the pile by larger displacement. So, you will get a load displacement relationship. So, if it is 80 ton and you have calculated 100 ton, you have to correct the design parameters to get 80 ton, use that reduced parameters to calculate what could be the increased penetration for 100 tons. So, that will be the future. So, all the new piles will be installed with 25 meters if you come up. So, that is the correction factors that you will apply. Testing based method, very expensive. I will show you the photographs of some of the pile load tests. It is very massive. I do not know whether you have seen somewhere in the Chennai city, some of the places pile load testing has been going on, but not recently. I think few months back the CMRL construction sites, metro site, they were doing few places, but now I think all removed. It is massive, because you have to mobilize so much dead weight to simulate the superstructure loading, and time consuming and occupies large space. So, it is a lot of trouble there. So, we have to minimize the number of testing, normally not more than 1 or 2 piles in a site, because of the cost and time. The next method is purely engineering based method. For example, if you have an onshore site, you could do this testing, no problem, because you can mobilize all this required. If it is a coastal site, also can be made, because you can construct a temporary platform by which you can do the loading. Whereas, if it is an offshore platform 100 meter water depth, doing testing by any means is impossible. For example, when you do a pile foundation for jacket, we cannot do testing. That means, we are going to 100% rely on what the engineering calculation has been carried out, and no testing can be possible, because of the nature of foundation and the depth of foundation, and we are installing a pile foundation through a jacket through which you cannot do testing. One of the biggest problem for testing is the reaction. I think every pile load that you apply, you need a reaction test frame, which is very difficult to make it in offshore. The testing we will talk about it I think later part. So, purely based on engineering design is going to be a challenge, because the amount of information you gather from the site is going to be used. So, the more information is better. So, that is where most of the offshore platforms we rely on engineering based design, whereas the coastal and onshore structures is testing, but not 100% tested, partially, and then we use that information to readjust the engineering, so that we can correct the mistakes. So, that is the idea behind the foundation design based on engineering. Is a very simple sequential task. The first thing is to establish the soil characteristics. So, that means the soil stratification at the site has to be established by historical means. You can actually look at what has happened over several years, or any particular construction activity in the recent times in that area, because you will get information with regards to soil boreholes. Also, when they were trying to do installation of piles in that vicinity, you could collect information on the old records. It will tell you whether it was hard driving or easy driving or the pile was going through easily, and then do a borehole at the site, collect information with regards to type of soil, strength characteristics either at the site or at the laboratory if you bring the soil back to the lab without disturbing, and then its deformation characteristics like Young's modulus. I think that is very important. So, you do a testing to establish relationship between stress and strain. So, once you do this for one particular and then look at the spatial variation, if you have more information. If you do not have information, then you are going to rely purely on one borehole. That is why most of the time for offshore structures we do the borehole exactly at the center of the platform itself, so that the distance to the all 4 piles are equally distributed. The risk involved in installing a pile also equally distributed, is not it. So, all 4 will have the same equal risk, but of course, if a soil varies within that 50 meter, as I mentioned earlier, it is a bad luck. Some projects it has happened, you know, in the last year we were having a jacket, only 4 main piles, 3 piles perfectly installed without any trouble, means has gone to the correct depth of design and stopped. The last pile it could not go more than 50%. So, we do not know within that 50 meter what has happened to that one corner, and that is exactly the nature of things that we are looking at. So, if you purely rely on engineering based design, you go offshore, you take 4 piles and just go and try to install, and one of them is not going. So, what happened to this jacket? You know, the jacket has to be downgraded, because it is not going does not mean that it has achieved sufficient capacity, because you might be using the capacity of the pile throughout the length, but the length is reduced, but of course increased base resistance. So, when you calculate the capacity, we found that it is not enough. So, because of this the foundation calculations, you actually can abandon the jacket, because it does not have sufficient strength to take the superstructure loads. So, such scenarios are very common. Because we could not do the testing, we rely highly on. So, you can imagine if they have done 4 boreholes at 4 corners, that would have been slightly better, but somebody wanted to save money, just because we do not want to do 4 boreholes, we will just do 1, and it still continue to be doing similar fashion. We do not want to do 4 boreholes, because it is time consuming. Every borehole will take 3 to 4 months to do, and laboratory and write report. So, again that means there is a risk always when you are designing a foundation for offshore structures. The risk is higher compared to onshore structures, because you are not doing pile load test. So, basically sometimes we do a back calculation during the driving of the pile. You can count the number of blows required to penetrate. For example, you take a nail, and if the nail is going through very easily, it indicates the soil is softer. If it goes very slow per blow, for example, for 100 blows it goes by very small distance, means the soil is denser. So, the relationship between the depth of penetration versus the number of blows required of a particular size of hammer, if you gather this information during driving, you will be able to correlate this back with the strength, because a lot of historical information is available. So, you can also calculate, but again empirical, because it is not going to be 100% similar to testing. So, the engineering based design has several uncertainties, I would say. Now, you could see the difference. If it is a testing based, the uncertainties has been removed by doing a testing, whereas you do not have testing. So, there is a large variation in soil characteristics going to happen if it is a larger structure, and because of that we need to apply a margin of safety. I think when we discussed about structural design is a well known characteristics of steel material, still we applied a margin of safety, where we divide the yield strength by 2 by 0.66 depending on nature of loading. We take only a fraction of yield strength as a strength material used for design purposes. So, similarly here we need to apply a factor of the strength of the soil at failure, and that will be the strength used for the calculation of foundation depth. That is called a factor of safety. And for different types of pile, different types of foundations, varying nature of factor safeties are recommended by codes experts, but for steel pipe piles for offshore applications, API recommends a minimum factor of 2. That means, you calculate the capacity as 100 tons at failure, ultimate failure, divide by 2 will be the load by which the foundation can take safely without excessive deformation. So, basically a factor of safety, a minimum of 2 is required. So, we are using 50%, very similar to what we were doing for structural steel calculations. We are using 66% for bending, axial 60%, shear 40%, I think you remember. So, similarly here we are going to use a 50% of the shear strength of the soil as the allowable capacity in comparison to the ultimate capacity at failure. But if you look at concrete piles or maybe other shallow foundations, different types of factor of safety, maybe they will allow 3, 4, sometimes some codes ask for 3. So, it depends on the uncertainties and the potential problem with failure, the risk of failure and type of structure. Residential buildings, you want to give a higher factor of safety, where the risk is higher for human life, whereas for the low class structures where there is no human activity, you can actually reduce the factor of safety, because only you are going to lose the property, but not human life. So, the engineering based design is the one that we are going to practice. Of course, we also will look at pile load testing, because some of the coastal structures you may require. What are the codes available? We will just go through some of them, and I think our course we will focus on API, because for steel tubular piles that is the only code available. But of course, you have other codes like board cast in situ piles IS 2911. There are 4 parts. I think it is available in our library also. And we also have board piles in rock. This is board pile in soil, either clay or sand, whereas board piles in rock is a separate code, because of the nature of load transfer between pile and the soil. Diaphragm walls, I think I have shown you some picture on the previous session. The diaphragm wall is nothing but a retaining wall, only difference is one side is water, the other side is soil. Very, very often used in port and harbor structures, which is just creating an interface between land and water, so that the ships can come closer. Diaphragm walls also used in onshore construction nowadays. You might have seen some of the high rise buildings, especially when they have a basement 2 or 3 levels of car park, you actually create a diaphragm wall as just very similar to retaining wall. And then the block work, basically I think I have shown you some picture of block work, simply pre-cast concrete blocks stacked and with proper shear keys, so that they just don't slide. So, that is, but basically the calculation here is the bearing capacity. When you stack very high block of say 10 meter, 20 meter, the total weight is acting on the seabed or the layer bearing. So, you need to look at the bearing capacity underwater. In some cases, some of the codes that I have mentioned here also specify some requirements for foundation, especially factor of safety. If you look at IS 4651 for port and harbors, the factor of safety is specified there. Similarly, the IS 9527 is the construction and practice, and then 6349 is a British code, of course, is also a maritime structures, which is applicable to coastal like port and harbors, jetties, wharves. So, you could see here collective information of codes. So, you need to just use it judicially according to the necessity and the type of structure that you are designing. So, we will focus predominantly on API RP2A, which is basically a code coming out of American Petroleum Institute, which is applicable to US waters, specifically for Gulf of Mexico. Most of the recommendations and the classification of soils are based on those area in Gulf of Mexico, but of course more generic. Many of them are reasonably generic that you can use it without much problem in other areas. Of course, if there is a special type of material, then we need to modify the procedure, not using blindly, it is quite obvious. We will just quickly look at how it is different onshore soil versus offshore soil. Basically, it depends basically on the sedimentary nature. Before we go into the layers of soil at the marine deposits, we just look at how the seabed varies and what are the activities related. And if you see this picture, will give you a better idea. Most of our human activities, especially the offshore oil and gas exploration, is very well limited to continental margin. I think if you have taken a, oceanography course is there, no? So you are going through, you will realize most of the human activities are very much limited to continental margin, at least in the last several decades. Slightly going into slight deeper water is also happening for, not for oil and gas reason, but also for mineral deposits. So you could see here the variation of the soil. I think I have shown two boreholes earlier, one from onshore to offshore, the other one is only onshore. So you see there some of the layers is actually purely sedimentary in the marine deposition area, whereas in the land or the interface area there could actually be a parent material. So that is why you will see that many times when you do a profile of the soil, some layers may actually exhibit in this area, some layers may there, but not necessary that the soil layers will actually go through the profile of the seabed, not necessary. So that you need to understand, because when you are doing a structure, for example, when you are doing a pipeline, you cannot assume that the soil layer will be exactly following the profile of the seabed, and that is why you will do a borehole. When you come closer and closer to the beach area, you will do a borehole very closer, because sometimes you will not have a specific soil profile. A typical area where you will find problem is this area, sometimes you will not even have that particular layer. So continental margin, ocean floor is quite far, sometimes you will have a oceanic ridge, something very similar like this, a shallow depth, but not protruding outside water. If it protrudes outside, it is actually becoming an island. That is what you will see in middle of ocean. Sometimes you see a small islands, it is just basically a ridge coming out. And depending on the location, the nature of deposits, the marine deposits will be differing. Basically the recent deposits, at least the last 10 to 15 meter deposits could be different. The reason why we need to know this profile, where is the activity higher, especially the wave and current, the disturbance of the soil is high in this region, because the shallow depth, most of the currents follow the coastal the profiles. So you will see that the rivers coming from onshore to offshore or onshore to mix with the sea is also going to bring lots and lots of materials from onshore and deposits. So the more deposition will happen very close to the coastline, because the particles will start settling down. Even if there is a velocity of flow, it will not carry for thousands of kilometers, because by the time almost all particles would have settled. So you can see here coarser material will settle here and less coarser material will get carried far away further to a deep ocean. So you will see a specific nature of particle sizing. If you just look at distance away from the coast, and if you go to a deep ocean, you will see the particle sizing is different than particle sizing close to the. At the same time, if you look at the depth wise, different timings, different particle sizing. So this kind of studies will give you a very good understanding what type of foundation is suitable. So as you can see here, 20% of the ocean floor is covered by continental margin, and it is reasonably enough for us to use it for so much of activities for hydrocarbons or for other minerals or coastal activity like port and harbors and so on. So, that we need to understand reasonably enough. How is soil made is obvious reason, you could easily find out. Basically is a breaking down of particle from larger size rocks or larger size parent earth. Several ways of breaking them down, either by environment or by mechanical or by biological, chemical. So, or combination of several of them. You take a rock, if you do a age study, you will find when it was actually formed, either from the parent material coming out of the earth or due to solidification of the lava. So, you can see one material breaks down either by environmental means due to wind or rain or heat and cold. Some several places temperature goes extremely like 50 degrees. If you go to Middle East, it goes to 50 degrees in the summer, and also summer itself in the night time it goes down to lower temperature. So, the large variation can break the rock into pieces if it is a weak rock, of course not the solid rock. Mechanical weathering, basically due to abrasion, human activities. When you actually have a smaller rock on the road, it gets broken down into smaller pieces if something is going on top, or other means, or you have a chemical weathering due to the chemicals present in the nature react with the silica available with the parent material. So, you could see here a variety of actions on the soil can create particle sizing depending on location, depending on which action makes and get carried by the primary form of transport is the river flow or by wind. Wind can carry large particles from one place to other, of course depending on the size. There are three processes we want to know as a geotechnical engineer. We do not want to know too much information about how the formation, but at least we need to know the origin by which because it is going to be used as a material for load transfer, especially if the material is biological in nature, how it will behave when you apply the loading. When it is mechanical process or chemical process, how it is going to affect the foundation. So, biological, basically change in chemical structure of the rock by a biochemical process. Growth of roots and plants, you might have seen in many places, and if you go to old temples, you will see that rock is broken just because of the growth of tree over a period of time, it just comes out, or animals doing damage to the existing systems. So, you just open it up, and basically biological process is very minimal damage. Mechanical weathering is the predominant form of forming particles of various sizes. Chemical in very isolated places, basically due to carbonization or basically oxidation of ferrous compounds present in the rock inside, basically trying to. So, during oxidation it actually becomes oxide and becomes porous, then the rock breaks. Mechanical process, I think several actions: heat and cold, frost, and basically salt weathering. If there is a salt present inside a rock and then it gets dissipated during evaporation, it can actually create the force inside the rock to come out. So, that is basic mechanical weathering. All this will be a combined form, it is not going to be one and like individual forms of disintegration of material. Marine sediments can be divided into three categories, as you can see here: lithogenous, predominantly silicate type of material, very similar to sand, that you can see a specific particle sizing. Biogenous, basically remains of animals, predominantly bones, and then hydrogenous is a material formed by basically chemical reactions. Out of all these three forms of formation process what we have discussed. Now, what we need to know is what it does. If it is a lithogenous, basically a silicate material, it is very good because it is not going to break down any further. Those particles can stay together when you apply loading, whereas these particles may break depending on the strength over a period of time. These hydrogenous particles are going to be slightly risky because they can get change in shape during the process of application of loading. So, when you actually look at soil borehole, the first thing you look at is the composition, whether it is silicate material or there is any other forms of material present in. So, you will do a chemical analysis to try and find out how much of silicates, how much of biogenous material is available, and then you look at any foreign particles in terms of chemical composition. The most important one is the carbonate material. Many of these areas near the beach or at least near the coastline within several kilometers, you find a lot of carbonate material, which will look like good silicate, dark in nature, but when you apply loading, it get crushed and becomes powder. So, that is the type of material causes a lot of failure to foundations because it was not identified during the investigation process. That is why nowadays almost all sites chemical processing of soil is compulsory to find out what is the composition irrespective of particle sizing.